Today I'm going to talk about a research paper that my colleagues and I at MongoDB wrote, which will be published in SIGMOD, and it's about a better way to make Raft consistent and also to recover faster from crashes. So for background, I'm going to just cover Raft in 5 minutes. Who here is familiar with Raft? I know Cockroach uses it. Okay, great. So this will be less than 5 minutes of Raft. It's a distributed algorithm to solve consensus. I think we know what that means. MongoDB had its own quasi-consensus algorithm before Raft was published in 2014, and it had some problems. And once Raft was published, we incorporated enough Raft to fix those problems. So now we are a Raft variant. In MongoDB, in most Rafts, there's a leader and 2 or more followers. They all have logs, and they also all have state. In our case, it's the database, and the goal is to eventually all have the same sequence of commands in the logs and the same state in the database. So yeah, I'm going to cover this. I know you know this, but we want to kind of get our brains in the same position. So in Raft, a client sends a command to the leader that does something like set x to 1. The leader knows that this command is not yet committed because a majority has not yet replicated it. So if the leader crashes now, the command will be forgotten forever. The leader then replicates it to followers. Let's say that the top follower replicates it first. The leader still doesn't know the command is committed until the follower acknowledges that command to the leader. Now the leader knows. The leader tracks something called a commit index, which is the position of the log that is majority replicated. So now the leader knows that C1 is committed, which means that it can execute it and update its state and safely acknowledge it to the client, because now the command will never be lost. Good. Now, what if the client sends a query to the leader? It's asking, like, what's the value of X? Everything works. The reply shows the result of command C1. So the client gets the read your rights guarantee, right? This is a consistency level. And Raft guarantees read your rights, except when there are elections. We'll see what that problem is soon. And just to finish up Raft, like, eventually the leader will tell the follower about the new commit index. Now the follower also knows that this command is committed, and it can also apply it to its copy of the data. In classic Raft, there are no follower reads, so the follower's state doesn't matter until it becomes a leader. And this lagging follower will probably eventually also learn about the command and learn that it's committed as well. So that's all we need to know about Raft right now. We don't need to worry about the election protocol or any of the other details. Now, how does Raft violate read your rights? Here's the scenario. So let's say that there's a network partition where the leader, after it's elected, loses its connection with the followers. But the client can still talk to both the leader and some of the followers. And this can really happen in a distributed system, right? It doesn't have to be a network misconfiguration. It could be one of the threads within a server is overloaded and it's lost its connection. One way or another, the client is seeing everybody, but they're not seeing each other. So one of the followers takes over and it becomes the leader in term 2. Raft allows multiple leaders at once. The thing that Raft guarantees is that every leader has a different term. So the client, even if it's doing only leader reads, it can execute a command on the leader of term 2 so that leader replicates it, acknowledges and commits and executes the command and acknowledges it back to the client. Okay, so far so good. And then the client sends its query to the old leader. And the old leader doesn't know about the new command, and so read your rights is violated. So this is the scenario in which Raft fails to guarantee read your rights. And in summary, the problem is when an old leader serves queries while a new leader is executing write commands. So this is the thing that we need to prevent in order to guarantee read your rights. Because Raft actually already prevents an old leader from committing rights. And I'm not going to explain how, you probably already know. This read from the old leader is the problem that we need to solve. Important technical thing, which you could ignore even though I'm saying it's important, is that if the client is reading from both of the leaders, it could bounce back and forth in time, and so monotonic reads is also violated. That's a different consistency guarantee. Leases also solve this problem. I'm going to talk about the read your rights guarantee because that's the kind of more straightforward example, but just keep in mind that there are two consistency guarantees that we are trying to promise here. And in this famous Jepson consistency graph of how the consistency levels depend on each other, we need both of those things at the bottom, monotonic reads and read your rights, because we are trying to guarantee linearizability or something strong like that in Raft. Okay, so forget about monotonic reads. We're just worrying about read your rights. And there are various ways to try to guarantee read your rights. There are unreliable ones, like the old leader just keeps checking if it can see a majority of the followers by exchanging messages with them. And if it loses touch with the majority for a few seconds, then it steps down. Raft recommends this, MongoDB does this. This works pretty well, but it's not reliable because of clock skew and message delays. We're not sure that this will prevent multiple simultaneous leaders all the time. Another unreliable method is that the leader can tell the client its term with every message, and then the client remembers the highest term it's seen. So in that other example we saw, the client talked to the leader of term 2, and then it talked to the leader of term 1. That should actually be prohibited. And MongoDB clients do have that check in them. The problem is clients can be restarted. You can be using multiple clients, each on its own thread. And also it doesn't work with sharding. That's MongoDB's data horizontal partitioning protocol. With sharding, clients are not talking directly to leaders, they're talking through routers. And if there are multiple routers in the system, they can have different views of what is the highest term leader. And so that can break that rule. So there are reliable and slow ways to guarantee read your rights. Basically what we need to do is that whenever a leader does a query, it checks with a majority of the followers, have you heard of a leader with a higher term than mine? If so, I will step down. If not, I will execute the client's query. But it has to do this for each query. I mean, it could maybe do some batching, but it's slow. The Raft paper actually recommends this. It's basically like a quorum read, and it makes reads as slow as writes because you have to do a network exchange with the majority of the followers for every single query. MongoDB has a very similar thing, but it's optional and turned off by default. If you, for an individual query, say that I want, we call it read concern linearizable, the leader will actually write a empty entry to the log and wait for it to be committed that proves that this leader was the highest term leader at that moment. And so then it executes the query and replies. So that works, but it's slow and people don't use it very much. here comes our superhero. Leader leases are fast and reliable. By the way, I know that Cockroach does use Raft with leases, but it's more complicated than this, and I get a little confused, and I also know that it's changed a little bit, so we can talk about that afterwards if you want to explain it to me. Leases were mentioned in the original Raft paper by Diego Ungaro, but it doesn't include any details. And then Ungaro's thesis has just this diagram and like a 1-paragraph English explanation, no code, no TLA plus. The algorithm is that so the leader is constantly talking to followers to tell them I'm still alive, don't elect somebody else. If you want to add leases to the protocol, you say, start a timer before you send out that round of heartbeats to your followers. Wait for a majority to reply. If any of them tell you that they've heard of a higher term leader, then you step down. If not, you know you're still the leader until some timeout. And then you keep extending your lease before that timeout expires so that you never lose it. Most Raft implementations of the wild, actually none of them do exactly this as far as I could find. Maybe Cockroach does, I don't know, tell me. But I didn't find any. And I think it's because it's really underspecified. It's just a paragraph of English. And in fact, when I tried to implement it, I realized that the leader is not sending heartbeats to all the followers at the same time. It actually needs to have a timer per follower and then do something slightly clever where it checks, have I heard from a majority of you recently? So it's really not well specified. And I think that's why most Raft implementations either don't do it or actually do it wrong. We found, like, including HashiCorp's Raft, we found Raft implementations had bugs and weren't actually guaranteeing what they thought they were with their lease algorithms. Yeah, so enter LeaseGuard. This is what my colleague Murat Demirbaş and I implemented last year and what we're publishing in SIGMOD. So it relies on a specific detail of Raft, which is the leader completeness guarantee. So in Raft, it's guaranteed that once a log entry is committed and a new leader is elected, the new leader already has that committed log entry in its log. So leaders are already complete and ready to serve consistent reads as soon as they're elected. Paxos doesn't promise this. View-stamped replication doesn't promise this. They have workarounds for electing incomplete leaders. They have to kind of go find the missing log entries from the cluster, but Raft has this specific simplification that they ensure through the election protocol that the leader is already complete. So we rely on this because what we realized is a server can look at its own log and its own commit index and infer things about what the other servers in the set know. And we'll see how this works concretely in a second. But it's like the log is a communication medium. It's a way of figuring out what other people know in the system. And so in our protocol, the log is the lease. We don't have separate lease extension messages. We don't have a lease data structure. The contents of the log tell you whether you have a lease or not, and whether anybody else has a lease. Okay, so here's the algorithm. Just like Cockroach does, we're going to assume that we have synchronized clocks with some known error-bound epsilon. And all the servers are already configured with some lease duration delta. And there are two rules, three. A leader can commit rights if all the entries in its log from previous terms are at least delta plus epsilon old. I will see this in a moment, but this is saying I can commit rights if nobody else has a lease still. So this is the lease timeout. And a leader can run queries if it has a committed entry in its own log that's less than delta old. So this is saying I have a lease and it has not timed out yet, right? This one, everybody else's leases are timed out. This one, my lease is not timed out. And then finally, there's a very complicated rule, which is that a leader must not run queries affected by commands in the limbo region. And that's our invention, and I will explain that in a couple of minutes. But first, let's look at these two rules again in a little bit of detail. So remember our goal. The goal is that a new leader can't commit rights while an old leader is running queries, because then those old queries would be stale. So we have these two rules. This rule says a new leader can commit rights if all previous term entries are more than delta old. So that means I was elected a leader. I already had a log full of entries that I replicated from other leaders when I was a follower. So my term is 2, and these log entries all have term 1, say. And they're all at least delta old. That means that I know that the old leaders who wrote those entries have stopped running queries. And then conversely, an old leader can run queries if it has any committed entry that's less than delta old, because it knows that any new leaders are following this rule. And so they still have entries that are too new. They know that my lease hasn't expired, so I can keep running queries. Takes a little while to get your head around, but these two things give you mutual exclusion among leaders. It means that only one leader believes it has the lease at a time. And there's no new messages. It's all just looking at your logs and measuring the age of the entries there. So the log is the lease. So that was our basic insight, is that we had this simplified lease algorithm. We tested it. We proved it was correct in TLA+. And then we've got 2 optimizations on top of it. And those are the main novelty of our paper. Number 1 is called deferred commit rights, which says that a new leader can do useful work while it's waiting for the lease. And then also inherited lease reads, which says that a new leader can actually run some queries while it's waiting for the lease. So these improve right, the recovery of right availability is faster with number 1, and then number 2 improves read availability during elections. And I'll describe these both in more detail. Oh, it doesn't. Yeah. Sorry, you're asking whether a leader knows if it's the new or the old leader, and obviously it doesn't. In fact, there might be any number of leaders with higher or lower terms than mine at any moment. Yeah, good question. So, optimization number 1, deferred commit rights. This is a great idea that was not our original invention. We saw some things like it previously. We're not like inventing cold fusion here. The idea is that a new leader can actually accept rights and send them to followers and get them acknowledged by followers, all while it's waiting for old leaders' leases to expire. Once it does get a lease, then it commits all of the rights that it already knows are majority replicated. So this reduces right unavailability because it's doing work while you're waiting for the lease, and so these rights are prepared. And so we can see an example of this in action. If we've got this situation, there's an old leader in term 1, and it still has the lease. And then there's a new leader, and the client knows about it and sends it a command. The new leader replicates it, receives the ACK from the follower, but it doesn't consider it committed, and so it doesn't execute it yet because it doesn't have a lease. Then once it gets the lease, it instantly knows that this command is committed and acknowledges it to the client that's waiting. If you've got thousands of commands piled up, while you're waiting half a second, say, for old lease to expire. This can really smooth out the load during a recovery. So that's the first. The second of the two optimizations is inherited read leases. This is the really novel and really complicated part of this protocol. And this was totally my colleague Murat's insight that this was possible. So the idea is the new leader runs queries while it's waiting to be sure that the old leader's lease is expired. So this seems to contradict everything that I just said, that the whole point of a lease is to prevent one leader from executing queries if another leader has a lease. The new leader has a way of knowing whether it's safe to do this or not on the individual query basis. And this reduces read unavailability because if the old leader actually crashed, the new leader can be serving reads while it's waiting to be sure about that. So here's how it works. We're in this situation once again. We've got an old leader with a lease, and the new leader in term 2 has just taken over. Now, they both have 3 commands in their logs, but notice that at the time that the network was partitioned, the leader in term 2 only knew that the commit index was 1. Leader 1 didn't have a chance to tell leader 2 that the commit index had advanced yet. So that means leader 2 knows that command 1 is definitely committed, but it doesn't know about those other commands. They might be committed, they might not be. So is leader 2 allowed to serve a query like this or not? Is this safe? It's only safe if leader 2 knows for sure that it has the same answer for Q that leader 1 would have. How can it know this? Well, all right, so that's where the term limbo region comes from. All of these commands that might be committed, but we don't know for sure, that's called the limbo region. So let's say that this is a key value store. And all of the commands just set X or Y to some value. And then the query is asking, what's the value for the key X? And leader 2 has to figure out, is this a safe query to execute or not? Well, it is in fact safe because leader 2 knows that setting X to 1 is committed and can also look at the log entries for the other 2 in the limbo region. They only affect key Y. And so it knows that it has the same answer for this query as leader 1 does. And so, yes, this is a safe limbo region query. And leader 2 can execute this even though it doesn't have a lease. On the other hand, if one of these commands affects X, which is the subject of the query, then leader 2 doesn't know whether that command is committed or not. And so it doesn't know if it has the same answer as leader 1, and so this is unsafe. Exactly. So you're asking, what if there are committed log entries from leader 1 that are not in leader 2's log? And Raft's leader completeness says that this is impossible, that in fact, if leader 1 has committed and executed a command, it is somewhere in leader 2's log. Leader 2 just doesn't know whether it's committed or not. Good question. And you can see why leader completeness, it's specific to Raft, and it's the foundation of this whole protocol. Right. Cool. So this is our big innovation. It's novel. It does require synchronized clocks, and you can read the paper for an explanation, which I know is not obvious from here, but this is where the synchronized clocks really come into play. It has to do with situations where there are many nodes that all think that they are leaders of various terms. Synchronized clocks are key to resolving that problem. You all probably are some of the experts on synchronized clocks in public clouds. To my knowledge, AWS rolled out time sync globally last year, and so we've got like 50 or 100 microsecond error bounds on clocks in AWS, and we actually know those error bounds, which is amazing. But the other clouds have not caught up. So relying on synchronized clocks is becoming possible and practical right now. Which is cool because it means that we can do research about it and it's very relevant. So I think this is sort of like the right part of the leading edge to be on for us, is to be exploring protocols that synchronized clocks make newly possible. Now, if the leader has a limbo region and it's just a simple key value store, then it's easy to just look at the log entries and tell, do these log entries affect the query result or not? But if you're a SQL database or if you're MongoDB and you have very complex queries, it's not obvious at all. Does this log entry affect the outcome of this query or not? So that's a topic for future research. I have benchmarks. So this shows how our optimizations improve read and write availability. The scenario here is, and this is, by the way, simulated. I wrote a Python simulation of the system. So at this time, the leader crashes while it's holding the lease. At this time, a new leader is elected, but I've set the lease timeout long enough that the old leader's lease expires later. So we've got half a second while we've got a new leader that doesn't own a lease yet. So how quickly does read and write throughput recover? Write throughput is in orange and read throughput is in blue. If you have no leases, then read and write throughput recover very quickly. And you can see them being a little bit elevated while some straggly clients are doing retries, and then it levels off again. But this is totally inconsistent. This does not guarantee read your writes. This is traditional leases where the new leader can't read or write for half a second after it's elected because it's waiting for the old lease to expire. And here you can see that reads are all rejected, so there's no read throughput. Writes are retried, and so they spike as soon as the lease expires, and then they settle down again. With the inherited read lease optimization, we can see that limbo reads are permitted instantly. Now, how much read throughput is permitted depends on how skewed your data access pattern is. If you've got a lot of queries and writes that are all using the same handful of keys, there might be a lot of rejected unsafe reads. But in this case, we've got a pretty sort of even key access pattern, and so read throughput recovers instantly, which is much faster than without this optimization. And then finally, in the full LeaseGuard implementation with deferred commit writes, you can see that whereas here it takes a while to work through the backlog of uncommitted writes when the new lease, when the new leader gets a lease, here it's already done all of that work. And so as soon as it has the lease, write throughput goes off the chart. It acknowledges all the writes at once. All of that acknowledgement traffic means that read traffic goes down for a second, and then everything recovers. So read and write throughput are significantly better with these two optimizations. We're almost done. As a researcher, I have to do this like defensive, neurotic thing where I say that what I did was better than anything anybody else has ever done before. So my thing's simpler. Like all leases, we guarantee read your rights with no extra latency. We improve read and write availability. We explore what's possible now with synchronized clocks. And we modeled it in TLA Plus and model checked it and showed that it works correctly. In the future, MongoDB is not actually going to implement this anytime soon. We've got, the thing is that we think that read your rights violations with MongoDB are incredibly rare. You have to have a number of unlucky things all happen at the same time. I'm guessing tens of billions of queries or more guarantee read your rights or do allow you to read your rights, even though it's not technically guaranteed by our protocol. So we have higher priority projects. So this is on the backlog right now. But the paper will be published in SIGMOD. And we're hoping that as the protocol becomes well known and people see that it's simple and finally we've got a really like thoroughly, precisely specified protocol, people will adopt it in existing Raft systems. And I'm going to SIGMOD, which is going to be in Bengaluru. So if anybody else is going, let's hang out and look at cool temples and eat hot curry. And final slide is further reading. I've got a blog post that describes all of this, and it also links to the paper itself. You can read. It's not published by SIGMOD yet, but it's uploaded to archive, so you can check out the details there. And you can ask me questions now, or you can email me. Thank you.